sometimes also called covalent compounds. Because the type of bond, the connection that keeps ionic compounds together is called ionic bonds, and what keeps molecular compounds together, they're called covalent bonds. And so molecular and covalent are interchangeable terms. For the most part, they tend to be smaller molecules, so we don't get into like organic chemistry where there's much larger components. And then even on the covalent side, we concentrate on binary ones, which means two numbers, and no more than two numbers. And so we keep it limited in scope, but it covers, in terms of types, but it covers some of the largest types in terms of vocabulary. And the chapter then starts first with ionic compounds. And so ionic compounds are made up of ions. In an ion, when an atom loses or gains electrons. So ions are charged atoms, charged particles. Atoms form positively charged ions when they lose electrons. Remember, the number of protons cannot change. So the only thing that can change is how many negatives you have. If you lose negatives, you start becoming positive because you have excess protons. If you gain negative ones, then you become negative because there's no proton to cancel this. And the electrons, if they're lost from somewhere, they have to go somewhere else. So we have to keep track of them. So if something is losing, something else has to be gained. Something becomes positive, something else becomes negative. And now you have electrostatic charges, and electrostatic charges attract each other, just like magnets. Positive attracts to negative. And that attraction, that electrostatic attraction between positive and negative charged particles creates ionic bonds. For covalent bonds, then we have the sharing of electrons. And both the gaining and losing and sharing of electrons occurs so that atoms can fill the shells. For the second row elements, then we're trying to get to 8. And that's where we have carbon, nitrogen, oxygen, fluorine, which are the compounds that we see most often in organic materials. Keep in mind, though, that when talking about transition metals, which we don't get too deep into, then that active rule can go out the window. Likewise, once we're in group 3 nonmetals, like sulfur and phosphorus, then the active rule does not have to be followed either, because the d orbitals are available. Either way, an ionic bond then occurs when electrons are transferred. And the rule of thumb is metals will lose electrons, nonmetals will gain electrons. So metals will become positive, nonmetals will become negative. That electrostatic attraction between the positive and negative components is an ionic bond. A covalent bond is formed though when electrons are shared between two nonmetals. And the electrons that are shared are used by both atoms to fill the shell. So, we have calcium. Okay, this is the electronic configuration of calcium. Okay. So, first shell is full, second shell is full, third shell is full. These we call vector electrons. The fourth shell, 4s and 4p, then it only has 2 electrons. The whole 4p section is empty. So the idea then is to have full shells. So calcium has the choice of getting 6 extra electrons and fill in the 4th level, or give up those 2 and revert back to what it already has for. Okay. For metals, then this is what happens. They'll give up this section to revert back to what's already for. So calcium will give up those 2 electrons and become a positive 2 ion. Oxygen.
Was that what you were telling us the other day, that they were more readily to give up their electrons and the other ones more readily to take on more?
Yes.
Which was the other one? Non-metals, right? Or
The nonmetals
will take on.
will take on. And so that's where oxygen comes in here. So oxygen needs 2 electrons to fill in its second shell. Or it can give up 6. Well, it's easier to gain 2 than to give up 6. Because basically it's just a question of numbers. And so these 2 electrons that were lost by calcium, oxygen can gain those 2 electrons. It fills that shell, and now we end up with an oxygen with negative 2.
With a negative 2?
And this always happens, right?
That transfers. The electrons have to go somewhere. There's always a charge balance.
A charge
And
balance.
that occurs in everything in nature. You cannot have positive ions without negative ions being in close proximity. Okay. Now, when you have very large distances in terms of separation, that can occur temporarily, and that's what these 2 like. You have that temporary charge separation, they end up being too far apart, but it's very high energy. And it doesn't last very long, and that high energy has to be released. They have to come back together and get that discharge of lightning and things explode and burn and stuff like that. Okay, so at the end, there always has to be a balance. You cannot have one without the other. Alkaline water. Part of the cell of alkaline water is that the water is charged. The water cannot be charged. Okay, now it can conduct electricity, it can contain electrolytes, it can contain positive and negative ions, but it contains an equal number of ones.
The same as
You cannot have water that's negatively charged or positively charged.
Wow.
Okay. I can stick this inside here, and I'm not going to get electrocuted
What the?
because I'm not closing the circuit.
Oh.
And so it's in. I'm not electrocuted. But I won't get electrocuted because you cannot have this without the other end.
So is it similar to, like in the magnet, the hyperpolarization, repolarization, depolarization?
It's more along the lines of channels. When you have a
Yeah, the
sodium channel,
because they have to go through the,
so if a sodium moves, something else.
comes in. Yeah, and then that's when you get into repolarization, because you've lost negatively charged ions, and then you gotta go back up.
And then now that you have the calcium and the oxygen, well, now these can make a bond, an ionic bond.
So does something have to cause this, or does it just happen? Because it's.
No, it happens because of the need to have functions. So it is, chemistry-wise, it is called, thermodynamically, it's spontaneous. Spontaneous, though, in chemistry doesn't mean fast. Spontaneous means that it will happen, or that it
Well, it's
happens.
guaranteed to happen.
Right.
How is that an ionic bond if oxygen is a non-metal? Isn't it?
No, so ionic just means that you have an attraction between 2 charged particles.
Because here it says it's the electrons of a metal atom are transferred.
Now are transferred to what?
I don't know.
So you don't have
I don't know.
That's half of the setup. So are transferred to,
Mm-hmm. Non-metal. Oh.
so these are electrons from here came over here.
Oh, I see.
So just generic examples. Okay. So on top, you can think of any group 1 metal. group 1 metals have one valence electron, they have one dot. So the blue sphere on top, that represents a group 1 metal. The yellow sphere represents a group 7 nonmetal. Group 7 nonmetals have 7 valence electrons, so they have 7 dots. So the group 1 will lose that S1 electron, and then revert back to the shell that's already full. Your nonmetal is missing 1 electron to fill that current shell. They're S2P5s. They want to be P6. So the metal gives up the electron, moves to the nonmetal. Now they both have full shells. The nonmetal has a brand new full shell, and metal has access to the one that it already had without that extra electron.
So they're still bonded even if it lost. I see. Okay.
Well, the charge attraction
Yeah.
is what makes the bond.
So it makes it more
Ooh.
stable when the outer shell is full.
Yes.
The charge attraction.
And that's what drives all spontaneous chemical reactions, the need for stability.
That's cool.
So even the universe is imbalanced. Because there's a need to be at lower energies. To be low in energy, the more stable, that's the natural state of things. But there's another component to that, which is entropy, which is disorder. And the second law of thermodynamics tells us that spontaneous processes increase entropy, increase disorder. So while the energy drops, it leads to more chaos. So you have stability, that leads to chaos. Which is proof by the math. It's not just talk. Okay. So, let's see, in ionic bonding, ions form when atoms gain and lose valence electrons from stable configuration. And so we have these patterns. Your group 1 are S1s. Your group 2 are S2s, group 3s. Okay. So 1 valence electron, 2 valence electrons, 3 valence electrons. So you either lose 1 or gain 7, lose 2 or gain 6, lose 3 or gain 5. That's the choice. So what involves the least number of electrons is what happens. So group 1 metals lose 1 electron and they become positive 1. Group 2 metals lose 2 valence electrons and become positive 2. Group 3 metals lose 3 valence electrons and become positive 3s.
So whenever they lose, it's positive, and when
Yes.
they gain,
It's just like the oxidizing and reduction kind of thing, or it's when you lose, you gain, and when you gain.
The loss of electrons is oxidation.
Yeah.
So your metals become oxidized and your non-metals become reduced.
Yes.
so is it metals or just elements in general?
Metals.
Like
No, for
That rule?
for losing.
electrons? No, for these rules are going to be the metals. Now, when you have a chemical, different types of chemical reactions will lead to different setups. So you can have metals gaining electrons.
Would that be the transitional metals
Yes.
that do weird stuff like that? Okay. Sorry.
But yeah, that's it. Well, in chapter 7, we're only going to cover moles, but we'll kind of skip types of chemical reactions. But in oxidation reduction reactions, a metal can oxidize another metal, and when it does that, it becomes reduced.
Oh.
So, for example, iron rusts.
Yes.
And in that process, when iron is rusting, it gives up 3 electrons in the process.
Okay.
It gives them up.
Gives up 3 electrons.
Yeah, because metals always give up.
And so in this case, oxygen is what process this you have.
Yeah.
But you have a thing called activity series for metals. And you can take, for example, a piece of zinc and you place it in a solution of copper. And the zinc becomes oxidized. And this copper right here, we're going to learn later on in the chapter, is a copper 2. That copper becomes a solid copper. So that the 2 electrons from zinc are transferred. Zinc loses 2 electrons, becomes positive 2. The positive 2 copper becomes 0. Becomes neutral.
0?
So here,
Does that mean neutral or just?
neutral, yes. Here, then you have copper gaining, well, a copper ion. Okay.
Oh, so it cancels out.
Right.
Oh.
Yes, we always have to keep track of electrons. Now we're gonna skip this part in chapter 7.
Thank you.
We won't have time to cover it.
Great.
Because at the end, I wanna get to IDs, to solutions.
Oh, that'll be fun.
So, from what we're doing here though, that rule of thumb is metals lose electrons, non-metals gain electrons. Okay. I just want you to be aware that that's not always the case.
Okay.
Okay.
So as far as the next test, we're going to be doing 6 and part of 7? Or you're not there yet?
No, yeah, 6 and like one section of 7.
Okay.
And so, just as an example, sodium has this pattern. Okay, it has 1 valence electron, and then it will lose that valence electron. So it starts with 1 is 2, 2 is 3, 3 is 6, 3 is 1.
Uh-huh.
So that's a 3. It's on the third row of the periodic table.
Uh-huh.
Gives up that 3s1 electron, now it has the first and second shell full. They were already full, but it was in the process of
Losing.
starting the next one. So it just would say, you know what, I'll give up filling that one and go back to what already there.
Okay.
Sodium's atomic number 11. 11 protons, 11 electrons. So you lose an electron, so now there's only 10 electrons. 11 minus 11 is 0. That's neutral. 11 minus 10 is a positive 1.
Mm. But then it only does that to bond with something else. So that's like the first step in bonding, correct?
Yes.
Okay, I got it.
So electrons are negative, that's why it becomes positive.
Yes. And then your nonmetals will do the opposite. Okay. So your metals revert back to what's already full. Your nonmetals. So your group 5 nonmetals, they're NS2 and 3, NS2 and 4, NS2 and 5. And to get to 8, we need to have T6. Okay, so I can give up 5 or gain 3. So group 5 nonmetals, they gain 3 electrons. We can do 6 or gain 2. So group 6 nonmetals, they gain 2 electrons. And then group 7, that 5 needs to become a 6, so they gain 1 electron. Right. So becomes -3, -2, and then that becomes a rule for the nonmetals. Group 7 nonmetals, -1, group 6 nonmetals, -2, group 5 nonmetals, -7.
I think I get it.
So group 1 plus 1, group 2 plus 2, group 3 metals, group 5 nonmetals, 3, group 6 nonmetals, -2, group 7 nonmetals. Okay, now very important for the negatives, as for the nonmetals. At the very bottom of group 5, we have antimony and something else. Which are metals, so that doesn't apply to those 2 metals.
Oh, okay. So only group 5 is that's where it happens?
Yeah, at group 6, you do have a metal at the very bottom, but that's like a man-made radioactive one, you won't see.
At the bottom. Group 6 has 1.
Now, for purposes of this is the actual chemistry, so there are no metals.
No metal?
You're either on the left-hand side of that staircase and you're a metal, or you're on the right-hand side of that staircase and you're a non-metal. Period.
So their metalloids can still do this, they're just not considered metal.
Right, because metalloids only happen when we take a look at physical properties. But now that we're transferring electrons, these are chemical properties. These are
Oh.
chemical reactions. So there's no metalloids. Metal, metalloids. That's it.
Okay.
So, in chapter 3, 4, we had a chart about the elements that are most prevalent in the body.
Oh, yeah.
And so we had carbon, nitrogen, oxygen, and hydrogen, and then we had your macro minerals, and then your micro minerals. So for the macro minerals, we have sodium, potassium, calcium, and magnesium. So these are the macro ones. And so where do we see them? And so outside the cell, that's where you have the analysis misspellings. Interstitial fluid, but the fluid between the cells.
Okay.
Intercellular fluid. Yes. And that's usually where you see sodium. And it regulates and controls basically the flow of water into and outside of the cells. So too much sodium and it can indicate a lack of water inside the cells, and sodium can indicate that it's dehydrated, more water. And sodium, you get it from everywhere. So it's, even in sweets. When you're making a cake,
You need it for
salt.
everything.
Salt is important. Potassium, principal cation, also just like sodium, though, but we need it in much more amounts. It's also part of regulation of body fluids and other functions, but it is also very important for cardiac functions, the cells in the heart. So potassium levels that are too low or too high are very critical for proper function of the heart. So potassium levels outside the normal range are the most critical ones of any one of those. So if you're too high on sodium or too low on sodium, it's not good, but it's not critical.
It's not gonna be.
Same thing with calcium or magnesium. But potassium levels outside the normal range, that's like an ER
Mm-hmm.
issue. Like something that you have to take care of. Right away. And so basically it can lead to a heart attack. Potassium chloride, which by the way it's added to, so table salt is sodium chloride. Okay. When you have low sodium salt, basically they mix in potassium chloride in. But when this is dissolved in water and injected into the bloodstream, it causes a heart attack. That's the second injection in, here in Texas, in the lethal injection.
Oh.
That's the second one that they give. The first one's a paralytic, starts slowing down the lungs. The second one, which is that one, they made a heart attack.
Hmm.
What's the third one?
Ooh.
Propofol, it's become a paralytic, stop the heart.
Propofol would be the heart.
First one's an anesthetic.
Aesthetic, yeah.
And stop the heart, and then the third one, I think, stops the lungs and the breathing.
That doesn't sound beautiful.
Well, they're asleep when it happens.
So yeah, very important.
They give them sleep.
Remember anything? You do electrolyte studies and you get
So
a
how
paper
can you-
back, and you see the potassium out of whack, you got to address
It's
it.
even like a point off, and then they're like in trouble. That's what they would always tell us in farm. Like a point counts. Like point whatever counts. Like every point
Well,
counts.
because potassium, like sodium,
But how do you get too much potassium?
We can, but it's like if your liver,
Well,
your
usually
kidneys
it's the
aren't
other way
functioning.
around. Usually it's gonna be too little.
Well, there's also medications that might do that, so they have to be really careful. It just depends. Like diabetes will cause that. Lots of stuff. Either too much or too little.
Runners, like 1 to 6
Uh-huh.
runners, things like that.
And that will even affect medications. Like if you're on antidepressants, just even your K levels being a little up will make them overdose like that. Yeah, it's crazy. Kidneys are nuts.
And then everything is relative to what normal is.
Mm-hmm. It's like a small range. I can't remember it now. I think it's like 3.4 or something.
So for sodium, you're in the 120s or 130s, I think. For potassium, you're in the low ones, like 3 to 5. So.
Yeah, I think it's 3.4 to 5 or something like that. I remember this because I got this question wrong on the test. I was like, ah, because every point counts. I was like, it's just one. It counted.
So it's kind of like your,
Well, there always has to be.
Like the kidneys are the boss of your body.
acidity, what is it called?
There's always a baseline. And so,
Alkaline and all that.
depending on what that baseline
When you're too alkaline.
Your pH, you mean? No, not with kidneys. Kidneys run everything.
Like as far as any little thing that's off. could cause you-
Well, your pH can move around a little bit. Not crazy, but it can. But it's more dangerous for your kidneys to move around a little bit. Your kidneys even control your lungs and your heart. It's weird.
So for sodium, normal levels, you're talking 135 to 145. Right. So, 1, 2 outside that range, that's less than 1% change. But for potassium, 3.5 to 1.5, plus 1 or minus 1, now you're talking, we're going to have a range 20%, 30% will be here below.
Mm-hmm.
So that 1 point that's out of the range, that's a 30% change in the normal is supposed to be. And so that it makes it more critical than before.
And the question I missed, it was like 5.6. I was like, it's just one. Nope. I killed my patient.
So write the formula symbol of an ion with 16 protons and 18 electrons. So you go on the periodic table, look up 16, and you're going to find sulfur. And so we take the protons minus electrons, and that equals a charge.
Electrons.
So we have 18 electrons in this problem, so we have a negative 2.
What's the first number? I can't see it. I think it's the glare. 16. 18. Ah, better. Thank you.
And I can turn it up because
Of the thing,
at
yeah.
first it was like a little bit. The charge goes on the top right.
Yeah.
So sulfur, 2.
And I noticed that you keep putting the negative on the right side. Is that a chemistry thing or?
And it's a time-saving thing. going back to when chemists were doing their dissertations, typewriters. So you didn't have computer where you can just highlight it, subscript, superscript.
So they'd have to write it with the two and fill in the is that what you mean? Or, oh, because there was no tiny, oh, okay, gotcha.
You know the old typewriters?
Yeah.
To do subscript, superscripts, you would roll it halfway and then type the number.
And hope it wasn't
And
like.
So you got this roller that rolls the paper to the next line. And on the mechanical ones, you got a lever and you would scoop the lever, and as the lever hit the other side, it would click to the next level.
Yeah.
Well, for like scientists, having to type stuff like this, you either would go back and with very nice handwriting, write it in, or you would have to roll it halfway and then get it out. And so it's an offset of necessity
Oh, okay.
for computers and for processes. So if you put it in front, like in terms of on a test, stuff like that, if you put it here, here's how to be.
Oh, okay.
Okay. On Pearson though, I do think
You have to do it
you have to put it under.
the chemistry way.
I'm not sure if it'll recognize it as something. All right, let's see. Consider the elements calcium and chlorine. So calcium, metal or non-metal?
Metal.
And chlorine?
Not metal.
So it's group 1, group 2, group 7. How many valence electrons for calcium? 2. How many for chlorine?
7.
Okay. So group 2 metals, what happens to the electrons?
They want
Get
to.
rid of them.
They get rid of them. So you lose 2. And for chlorine,
You gain them.
how many?
7.
One.
Remember, 1 to get to 8. So you
Oh,
get
1.
7. And remember, this 7 is 2 plus 1.
Yeah.
So group 1 plus 1, group 2 plus 2, group 3 plus 3. Group 7 nonmetals, -1, group 6 nonmetals, -2, group 5 nonmetals, -2. So 1, 2, 3, -1, -2, -2. And so you write the symbol, then you got calcium 2 plus, chlorine, and usually the negative, the 1 is omitted. So if you just have the sign plus or minus, it means 1. And then real quick, in terms of positive ions are called anions, and negative ions are called anions. The cathode terminal on a battery is a positive terminal. The anode terminal on a battery is a negative. So since there always has to be a balance, the gaining, the losing gaining of electrons is not always on a 1-to-1 ratio. So the example where calcium gave up 2 and oxygen gained 2, then use 1 calcium, 1 oxygen. That's not always the case. So as an example here, we have calcium giving up 2 electrons and chlorine gaining only 1. So if these are to combine in a compound, then there has to be a charge balance also, which means we would need 2 chlorines. Since this is giving up 2 electrons, 1 electron goes here, the other electron goes here.
That one stays with 1.
And then the formula would be CaCO2. So in ionic compounds, you need to have an equal number of positives as you do negatives. in order to
What the hell
make
happened?
a compound. So compound means neutral. Ionic compounds consist of positive and negative charges, basically metals and nonmetals, held together by strong electrostatic attractions. Positives, opposites attract. The idea is to get the right combination so that it's neutral. Those electrostatic attractions are very strong. That makes ionic compounds have very high melting and boiling points.
Oh, the attraction is
All
strong.
ionic compounds are solids at room temperature. All of them. And the word salt is a generic term for an ionic compound. So ionic compounds are salts. Salts means an ionic compound. Table salt, CL, sodium with a positive one charge, Cl with a negative one charge. So we combine the two into a chemical formula, then we write it as NaCl. Keep in mind that in the actual structure, all ionic compounds crystallize, they form crystals. You don't have like one in one, then another set of one in one, another set of one in one. But you have a network of positive ions. The interface with a network of negative ions. Now overall it's a 1-to-1 ratio, but within the network, you have attractions between all. The actual structure, the real structure of those crystals, it's a network of positive and negative ions interchange. But when you take accounting of all of them, it ends up being a 1-to-1 ratio for sodium chloride. Or something like calcium chloride, then it ends up being a 2-to-1 ratio. But it's still a network, which is not what happens with covalent compounds. In covalent compounds, when you see the formula, that formula is its own entity.
Oh, okay. So when we're talking about ionic, the subscript will tell you the ratio? Is it safe to say that? Okay.
Yes. And if you're coming up with a formula, then you have to provide that subscript. If there's
Oh.
positive 1 cancels a negative 1, and we end up with. Now, real quick, in terms of the diagrams, when sodium gives up that electron, it's losing a shell, so its size decreases.
Mm.
So when metals go from neutral to positive, they always shrink.
Yeah, that makes
Because you're
sense.
losing that valency.
The ring.
Non-metals, when they gain electrons, they increase in size. You're gaining a negative charge, but you don't have the proton to bring it in. So it's held very loosely. Basically, and think of it as a magnet. So chlorine here has 17 protons and 17 electrons. So the positive to negative, it's a 1-to-1. Right. But once it gains that electron, now that ratio if we divide 17 divided by 18 is 0.94 to 1. Basically, what that means, every electron here is feeling 100% of the attraction from a proton. Every electron here is only feeling about 94% of that attraction. So it's 6% more loose.
Bigger.
So it can go a little bit further away.
Oh. So when it's less than 100, it's going to be bigger, and when it's more than 100, it's going to be smaller? Is that correct to assume?
Yes, and that's what happens with sodium.
Mm.
With sodium, now you have 11 protons and 10 electrons. And then you have a 1.1 ratio.
Oh, wow.
So
That's
sodium shrinks, your metals will shrink as they become positive, your nonmetals increase in size. That's it.
How did you figure the difference again? You divided 17 from 18? And then in
Yes,
that
divided
case,
by 10.
and then 11 divided by 10. Okay. Let me write this down.
So, now we got earlier with calcium chloride. Magnesium is in group 2, so this is 2 electrons. They have to go somewhere. If we're combining it with chlorine, each chlorine can only gain 1. So we end up with a need for 2 to balance that. Okay, but at the end, it has to be neutral. Positive 2 minus 2 negatives gives a 0.
So are these an ionic bond?
Yes. And then MgCl2, that's in ionic formula. Sometimes a positive is bigger than a negative, sometimes a negative is bigger than a positive. So we have sulfur, which is in group 6. Group 6 nonmetals are -2. Sodium group 1, group 1 is positive 1. So you need 2 positive 1s to cancel the negative 2 and so on. And then the formula becomes Na2. Yes. How many negative 1s to cancel a positive 2? 2. So the formula is BaCO2. So positive 2 times 1 is 2. Negative 1 times 2 is negative 2. And where is it? Formula for barium and chlorine is BaCO2. Barium is +2 because it's in group 2. Cl is -1 because it's in group 7. Group 7 -1, group 6 -2, group 5 -3. How many positive 1s to cancel a negative 2? This 2 is telling me 2 sodiums.
Oh.
So it's positive 2, negative 2, then 0. How many negative 1s to cancel a positive 3?
What was the question? How many positive ones?
How many negatives
Negative ones, 3.
to cancel a positive?
Oh.
What is the lowest common multiple
Ugh.
between 2 and 3? How many 2's to get to 6?
3,
How many 3's to get to 6?
2.
First, you find the lowest common multiple.
And then how many do you need to get to that? These are like puzzle pieces. So positive 1's was 1 electron, positive 2's was 2 electrons, positive 3's was 3 electrons, negative 1's 1, negative 2's 2, negative 3's. So here we're trying to put together 2's and 3's. They don't match up. So I bring in another plus 2. Well, it's still not matching up, so I bring in another plus 3. It's even negative. Still not matching up. Bring in another positive 2.
Oh, that's nice.
So you have 1, 2, 3 positive 2's. 1, 2. Negative 3.
That makes sense.
Yes, no, maybe. Positive 3, so you have one of these.
So you're gonna have the whole compound is basically.
So those work out real nice.
So here Al3, it's that and that. So I have 3 holes. So I need 3 of these. One there, one there, one there.
No.
This, now, if yes, so the,
Denominator, isn't it multiple? It is? Oh,
when working with fractions, we call it this.
okay.
If we're not working with fractions, we call it a multiple. Okay. But, yeah, so if you want to add halves and thirds, then the lowest common denominator is 6. So you would have to turn that into 6 and that into 6.
Oh,
So you multiply that times 3 over 3, multiply that times 2 over 2. So yes, that will always. If you've done some of this, some of you may crisscross. Crisscross doesn't always work. But the lowest common denominator always works.
and then so it loses its negative charge, I noticed in the last one. Does that always
Well,
happen?
no, they're there, but in the full formula, it's not shown because they neutralized each other.
Okay,
Because the compounds always have to be neutral.
okay.
So you don't do right.
Got it.
Okay, so what do we have? B, A, now the tricky one. Naming the compounds.
Name?
Yes. So this has a name, that has a name. So AI, for example, start with SMI. Which is hard to solve because it's very difficult for us to get enough biomass from natural sources. So it's artificially able to solve. It's not part of kosher salt, so you make kosher salt.
It's not part of sea salt either.
Right. Okay, we're naming an ionic compound. Now, the very first thing is, how do you know it's ionic?
Yeah,
Because
the chart.
we have to, right now we're doing ionic, but later on in the chapter, we're also going to do molecular. So your if it begins with a metal or ammonia, okay? And whether it's the name or the formula, if you have the name, it's the first part of the name of a metal, or does it begin with the word ammonia? If you have the formula, then it's the first element in that formula a metal, or is that first part NH4? If the answer is yes, then we have an ionic compound. If the answer is no, it's not ionic and none of these rules apply. This is only for ionic compounds. Ionic compounds are made up of two parts, the positive part and the negative part, the cation and the anion. So on the metal side, there's going to be two different types of metals. A monovalent metal. And ammonium belongs in that set. Mono meaning one, valence, basically these metals and ammonia, they always have the same, when they're part of an ionic compound, they always have the same charge. Group 1 metals will always be +1, group 2 will always be +2, group 3 will always be +3. Zinc and cadmium will always be +2. Silver will always be +1, and then ammonia, it's not a metal, but it behaves like a group 1 metal, it's always +1. So we can always determine what the charge is. Based on group 1 +1, group 2 +2, group 3 +3. Zinc, cadmium, and silver, you have to memorize those.
Just those two?
And
Or
zinc, cadmium, and silver. So zinc and cadmium are always +2, silver is always +3. So they will always, when they're part of an ionic compound, they always have that charge. Always, 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 no exceptions.
So this has to do with the charge, not the name.
Well, the charge determines how we do it. Or, yeah. Any metal that is not on that list, basically your transition rules. They're multivalent. That means that they come in different forms. Like iron comes in a +2 and a +3 form. Copper comes as +1, +2, +3. Chromium, all the way from +1 to +6. +1, +2. So they, in different compounds, they can have different charges. So if you have the formula and are trying to come up with a name, you have to calculate what the charge is. and then include it in the name using a Roman numeral in parentheses. If you have the name, then the name will tell you what the church is because it will have that Roman numeral in parentheses. So it'll say iron 1, which means plus 1, iron 2 means iron plus 2, iron 3, iron plus 2. So the name will tell you. If you have the formula, you have to include the charge. That's it. So for the monovalent ones, you just write the name of the metal. Here you write the name of the metal and the charge in parentheses using a Roman. These don't need a Roman numeral because we're supposed to know what they are. This, the name needs to tell me so I know which version it is. Write the name, that's it. Name plus a Roman numeral. On the negative side, so the first part is just name of the metal. On the negative side, if it's a non-metal, the ending is going to change to IDE. So there's two types of negative ions too. You have your monoatomic, and this means it's a non-metal. Group 7, -1. 6, 2, 5, and you change the ending to ID. Fluorine becomes fluoride, chlorine becomes chloride, oxygen becomes oxide, sulfur becomes sulfide, so on and so forth.
So those are all common.
It's not monatomic, and monatomic means one non-metal. You can have a subscript. That can have 2, 3, but it'll be 2 or 3 of the same kind. The same one. Or it can be polyatomic. If it's polyatomic, it's going to be on that handout, that second handout that you use on the first exam.
Oh.
That we haven't used.
Till we minimize real small.
So the handout table gives you the name, the charge, and the formula. And almost all of them end in either ATE or IT.
Okay.
The first set, monovalent with monatomic are the easiest. Name the metal, name the non-metal, make sure it's an IDE, and that's it. Don't worry about subscripts. Don't worry about Roman numerals. Just name the two parts, and that's it, that's it, that's it, that's it, that's it. Okay, don't complicate it.
So on the monovalent, you just name the metal with what?
If the negative side is one of these, then name the non-metal.
With ID.
You can make sure it's an ID. And that's it. Doesn't matter if you have subscripts or not. Group 1 metal, group 2 metal, group 3 metal. Group 1, group 2, group 3. That's a non-metal. Iodine becomes iodide. Bromine becomes bromide. Oxygen becomes oxide. Potassium, iodide. Magnesium, bromide. Aluminum oxide. That's it. Name the metal, name the non-metal, make sure it's an IDE, and that's it. That's it. That's it. That's it. That's it.
So there's no change.
Don't
on
worry
the-
about that 2. Don't worry about that 2 and that 3.
Okay.
This is just, no change on monovalent.
There's enough information. Chemists are lazy. The minimum amount of information to get the job done. That's all we need. We don't want to write extra letters, extra symbols, or things that become redundant. There's enough information here for us to figure out the formula from the rules. So if we have potassium iodide, well, if I know potassium's in group 1, I know it's +1. And I know that iodine is in group 7, which is a -1. Positive 1 cancels a -1, and the formula is Ki. So I have all the information that I need to figure out the formula. Aluminum oxide. I know that aluminum is in group 3, so it's +3. I know that oxygen is in group 6, that makes it a -2. Right, the lowest common multiple denominator is 6. How many 3's to get to 6? How many 2's to get to 6? So from the name aluminum oxide, I have everything I need to figure this out. Questions? Now, you do need to remember +1, +2, +3. -1, -2, -1.
Is that CD2?
And they're together in the periodic table, cadmium, silver, and zinc. They make a backwards L. +2, +2, +1.
And where's the NH?
Ammonium, that one's on the ammonium because this is polyatomic.
Oh,
But on this list, all of them are negative, except for that. That's the one positive that's on that list. And that is on your hand.
Awesome.
So, K, what's the name of K?
Potassium
Oxygen becomes,
oxide.
that's it, potassium oxide. Group 1, group 6. Group 1, group 6. That's it, potassium oxide. That's it. So Ca is
Calcium.
calcium oxide.
Al is aluminum,
Oxide.
Mg,
And it's chloride.
calcium oxide, aluminum oxide, magnesium. In the metal, in the non-metal, make sure it's an ID. Now, real quick, sulfur becomes sulfide, not sulfuride, sulfide. Potassium, phosphorus becomes phosphide, not a phosphoride. So sulfur, sulfide, phosphorus, phosphide.
Well, I guess you would just think like you've never heard of sulfuride, but you've heard of sulfide.
Sometimes you think.
I've never heard of sulfuride. I've heard of sulfide.
So sulfide, and what was the other one? Lisa?
Phosphorus becomes phosphide. Phosphide.
Oh, I knew it. I got that right.
So NABR plus 1 cancels a -1. So it's just one of each, NABR. NaNS2, you need 2 positive ones to cancel the -2 in sulfur. So we need 2 sodiums, so it's Na2S. And then we need 3 positive ones to cancel a -3, so it's Na3N.
Oh, okay.
Plus 1 minus 1, you need 2 positive ones to cancel the -2. You need 3 positive ones to cancel the -2. The name of this ion is sodium. That's it, sodium. Bromine becomes bromide, sulfur becomes sulfide, nitrogen becomes nitride. And so you just name the 2, sodium bromide, sodium sulfide, sodium nitride. Don't worry about those substances.
So I noticed
Work
it's,
it backwards, they take care of themselves.
I noticed you put nitride. I've heard of sodium nitrate. Is that, nope, don't do it. Oh, got it. Okay.
That's something else.
Okay.
And then same thing on the bottom. I need 3 -1s to cancel the +3. There you go here. 3s and 2s, we need to get to 6. So I need 2 +3s. That gives me +6. I need 3 -2s. That gives me -6. +6 cancels a -6. And then a +3 cancels a -3. +3 cancels a -3, so just need 1 of each. And then that's aluminum, bromide, aluminum sulfide, aluminum nitride. DE, don't worry about the substance.
Okay,
Just name the metal, name the non-metal.
get it over with.
Okay, when we're doing these combinations right here.
Not too crazy.
Okay, we'll leave it there, and then next time we'll do one word. We have to do a little bit more.